Okay, in this video, we're going to talk about spherical mirrors. Light incident can come from a distant object, and so the farther away the object is, the more parallel those rays appear to be to somebody viewing them very far away. So to develop an understanding of how images are formed by any lens or mirror, it's useful to understand that those light rays coming in from a distant object can appear to be effectively parallel. So as you can see, very distant object, the rays are coming out, but look at what's actually hitting the mirror. They appear to be parallel to one another. So the farther away you are from an object that's giving you the object you're trying to form an image of, the more parallel those rays appear to the optic. Spherical mirrors are shaped like sections of a sphere and may be reflective on either side. So they can be reflective on the inside of the sphere or on the outside of the sphere. If the reflective surface is on the inside of the mirror, we call that concave, and that's because it appears to be a cave opening. If the reflective surface is on the outside, like it is in this picture, then the mirror is called convex. Parallel incident rays reflect and converge, as you can see here. We call this a real focal point. That's where the rays come to a focus. The distance between the mirror and that focal point is called the focal length. Parallel incident rays reflect and diverge for a convex mirror. So notice that these light purple rays never appear to cross one another. If we take them back in space, they would actually appear to cross right here, and we call this a virtual focal point or a negative focal point. So when we can actually converge the rays physically to the point where we could actually put a piece of paper here, we call that a real focal point. If it appears to come from inside the mirror or the optic, we call that a virtual focal point. When describing and working with spherical mirrors, there are two important points and their corresponding distances from the mirror. So C is called the center of curvature. This is the center of the completed sphere. So if we were to take the mirror and go all the way around, C would be at the center. That means that any light ray that goes through C and hits the mirror will come right back out through C. And that's because any light ray coming from C to the optic is going to be perpendicular to its surface, and that means it's going to reflect right back in on itself. Okay, the radius of curvature is the distance from C to the mirror. Okay, so the center of curvature is the point C. The radius of curvature is the distance between C and the mirror. F is the focal point. This is where the light rays converge. F, the little f, is the focal length, and you can see the picture right here. So the distance between C and the mirror is R, the radius of curvature. From the distance from the focal point to the mirror is called the focal length. The line that passes through C and F we call the principal axis of the mirror. Okay, they just wrote here the axis, but we usually say the principal axis because it's the main axis that we're drawing our diagrams on. The focal length of a spherical mirror is actually half of the radius of curvature. So there's a relationship between the focal length and the radius of curvature. For mirrors with large curvatures, parallel rays do not always converge at the exact same point. We call this a spherical aberration, as you can see here. If the curvature is small, the focus is much more precise, and the spherical aberration can be neglected. So you can see there's a slight aberration here, but we've been able to eliminate it by making the curvature smaller. We can use ray diagrams to determine where the image will form when using a spherical mirror. There are three principal lines that we're going to draw, three rays. The first ray is parallel to the principal axis, and then after it reflects, it goes through the focal point. The second ray passes through the focal point, and then after reflection, exits parallel to the principal axis. The third ray will go through the center of curvature and back out again. So this is a light ray that's perpendicular. A ray that strikes the mirror at the principal axis and at a certain angle and reflects back at the same angle. Okay, so that's the same thing. If we have a light ray that strikes along the principal axis, it's going to come right back out at the same angle. A ray that is first parallel to the axis and then after reflection passes through the focal point looks like this. So notice here the ray goes parallel to the principal axis through the focal point. A ray that passes through the focal point and then after reflection is parallel. Goes through the focal point, comes out parallel. The third ray goes through the center of curvature and goes back out again along that same line. Where these three rays intersect, that is the image of the point that we just drew the three light rays from. So since we're drawing the three light rays from the tip of the arrow of our object, that's what we're forming. We're forming an image of the tip of the arrow at that point. A ray that strikes the mirror at the principal axis and at a certain angle will reflect back through at that angle, as you can see here. So that's a fourth ray that you can draw. You really only need 2 rays to form an image, but the more rays you draw, the better chance you have of having a correct image drawn. Again, only 2 rays are needed to find the image, but it's also useful to draw 1 or 2 more. When the object is in between the center of curvature and the focal point, your image is going to be magnified, real, and inverted. Here's the trick. Anytime your image formed is inverted, upside down, it's going to be real. Okay, so anytime you are beyond the focal point, anywhere out here, you're going to form a real image with a concave mirror. We can derive an equation that relates the object distance, the image distance, and the focal length by using the following. I call it the mirror lens equation because it's the same for both optics. So it's 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. So let's look at that. I want to go ahead and show you what each one of these looks like. So we'll do this. And let's make it a color that we can see that's different. Okay, so the distance between the object and the mirror is called DO. I'll put that right there so you can see it. Okay, let's change the color again. The distance from F to the mirror is called the focal length. Okay. And let's go ahead and pick a different color. And the distance between the image and the mirror is called the image distance DI. You physically measure this with a ruler. You physically measure this with a ruler. You physically measure this with a ruler. Now I'm going to give you a little hint. When we do these ray diagrams, we never use an actual curve. We actually just use a very straight line. And we draw everything from the straight line. You can only do the straight line if you are working with very thin optics. Okay, so if you're working with very thin optics, you can use a straight line, a straight vertical line to indicate the mirror or the lens. We can also derive an equation that relates the object distance, image distance, and the magnification. The magnification is equal to the image height divided by the object height. But it's also equal to the negative. And let me draw this like this. Because a lot of times students will say, oh, it's a negative DI, so that negative takes care of it. And that's not what it means. If you get a negative DI, you put a negative DI in here. And then you put a DO in here, and then a negative times a negative gives you a positive magnification. Okay. Now, the negative sign indicates that the image is inverted. So if we do not need to use the negative sign, well, when we're doing the ray diagrams, we don't need to use the negative sign because we look at the picture. It's either going to be upright or it's going to be inverted. But when you're doing these problems mathematically, you can't necessarily see whether the image is inverted or not. So if we get a negative magnification, that means it's inverted, and that means it's a real image. If we get a positive magnification, that tells us that we are dealing with a virtual image. In other words, it's upright, and it's going to be virtual. If the object is past the center of curvature, we're going to first draw the ray parallel and then through the focal point as shown. You then draw one through the through the focal point out parallel. Then you draw it through the center of curvature, which should go like this. Notice it's a little bit off on their drawing. Okay, so you could do it through the center of curvature, and then the last one would be hit the principal axis, come back at the same angle. That's kind of tricky because you actually have to measure that. But with the first three rays, you don't have to measure any angles at all. Okay, so notice that this image is going to be inverted, which makes it real, but notice it's actually smaller. If the object is inside the focal point, the first ray drawn is going to be parallel to the principal axis and through the focal point. The second ray is going to go through the focal point and come out parallel. This is a little bit tricky, okay, because the focal point is actually behind the object. Notice that when we take these two rays, these two exiting rays, and I want to circle them so you see this. Okay, you're using these two rays to form your image. Notice that they appear to come from out here, in here. Okay, I don't like that they put arrows on that. That's not right. These shouldn't have any arrows at all. So I'm going to get rid of the arrow. Because an arrow usually indicates that it's an actual physical light ray. These are not. We're actually just projecting these reflected light rays back into the mirror. Okay, so notice that we are forming something that is upright. It is larger, and because it's upright with respect to the image or to the object, it's going to be virtual. So it's magnified, it's larger, it's virtual because it's inside the mirror, and it's upright. If the object is in front of the convex mirror, you're going to notice something here. You're going to put the focal point and the center of curvature inside the mirror. So they're going to go on the right-hand side. That means that these are virtual. So that means that the focal point is virtual. The center of curvature is virtual. So when you substitute this number into your mirror equation, 1 over f equals 1 over di plus 1 over do, you're going to have to put a negative in front of the f for your calculations. So the first thing we're going to do is draw a ray that's parallel to the principal axis and then has to go through the focal point. Okay, so parallel through the focal point. Again, this is one of those tricky rays. The next one goes through the focal point, hits the mirror before it actually goes into the focal point, because this isn't really here, and comes out parallel. Okay, notice that these two rays do not intersect, just like the previous example with the concave mirror. But if we were to project them back into space, they do appear to cross right back in here. And that crossing point where these two appear to cross, this is where your virtual image will be formed. Okay, so notice that this image is smaller, it's upright, and it's inside the mirror, so that makes it virtual. A ray of light strikes a convex mirror parallel to the central axis, or the principal axis. Which of the following represent the reflected ray? Is it A, B, C, or D? Okay, let's check your answer. Hopefully you chose B. A ray of light strikes a concave mirror parallel to the principal axis. Which of the following represents the reflected ray? Okay, hopefully you picked A. A candle is placed in front of a concave mirror between the center of curvature and the focal point. Describe the image. Is it real inverted magnified, real inverted demagnified, virtual upright magnified, virtual upright demagnified? Okay, so let's check your answer. Hopefully you chose A. A candle with a height of 6 centimeters is placed 21 centimeters in front of a concave mirror that has a focal length of 7 centimeters. How far is the image from the mirror? Go ahead and pause the video now. Okay, so let's take a look at the answer. We're going to use the formula 1 over F equals 1 over DI plus 1 over DO. We're going to manipulate algebraically to solve for 1 over DI, substitute in our numbers, and we end up with the image distance is equal to 10.5 or 11 centimeters if you go by sig figs. Actually, it's kind of tricky because it's 1 over 7. But then we subtract, so maybe that's okay. A candle with a height of 6 centimeters is placed 21 centimeters in front of a concave mirror with a focal length of 7 centimeters. How tall is the image? Okay, go ahead and pause your video. Okay, so let's take a look. We know that the image distance from the previous example is 10.5. The object distance is 21 centimeters. We know that the object height is 6 centimeters. And we also know that there's a relationship between image height, image distance, and object distance, which is called the magnification. So we're getting rid of the negative sign here because we're only interested in the height. We're not interested in the direction of the height. We don't care whether it's inverted or upright. Okay, so substituting in our numbers, we end up with an image height of 3 centimeters. So it's going to be smaller or demagnified. Which of the following indicates the image distance DI for an object that is placed in front of a concave mirror if the image created is inverted? There are 2 answers. Okay, so let's take a look and see if you have the right answers. If you need more time, please pause the video. Okay, the correct answers are B and C. If you're between 2F and F, or you are greater than 2F, then you will form an image that is inverted. The only time you do not form a real image when you're working with a concave mirror is if you are within the focal length of the mirror. Okay, in the next video, we're going to talk about refraction and Snell's law.